Hello my dears. So in the last class we discussed about what? I think the concept of surge impedance and surge impedance loading, etc. Right? And we discussed some important fact also. If the loading is less than the surge impedance loading, then it will be the capacitive, right? QC greater than QL will be there. So the power factor of the line will be at that time leading power factor, right? So like that we discussed something very important things. So today, as the continuation of tomorrow's class, yesterday's class, so now we are going to discuss another important term, which is nothing but propagation constant. What my dears? Propagation constant. It is represented by gamma. It is represented by gamma. So listen, so yesterday we discussed the characteristic impedance equation, that is nothing but root of z by y. But what if root of z into y means? What if root of z into y means? That is called gamma. This gamma is called the propagation constant. Okay, propagation constant. Gamma is called the propagation constant. And we know that, my dears, this gamma is equal to what is z? R plus j omega n, right? And what is y? G plus jb. Jb is nothing but g plus j omega c, right? G plus j omega c. And this is the gamma. So this will be in the form of, my dear, gamma is equal to, if you solve this, definitely you will obtain the form of alpha plus j beta. What is that? Alpha plus j beta form you will get, and this alpha is called the attenuation constant, and beta you called it as phase constant, my dear, phase constant. And the attenuation constant will be represented in dB or Nepper per length. dB or Nepper per length. And this phase constant is nothing but, my dear, radian per length. Radian per length. And for lossless transmission line, this is called at propagation constant. The propagation constant consists of attenuation plus phase constant, my dears. Propagation constant consists of attenuation plus phase constant. It's similar equation we already derived in the control system also, right? So for lossless transmission line, my dears, lossless transmission line, we already discussed what? R will be equal to 0 and G will be equal to 0. Am I right? R will be equal to 0 and G will be equal to 0. So our gamma will become root of 0 plus j omega L into again j omega C. So if I take j omega common, j omega square, so j square omega square, j omega common outside, simply root of LC, right? So it is nothing but, my dear, gamma is equal to 0 plus j into omega root LC form, right? Which means here the alpha will be equal to 0 and beta will be nothing but, my dear, omega root of LC. So this is for the what? Lossless transmission line. So for lossless transmission line, there will not be any propagation constant, my dear. There will not be any propagation constant. Only phase constant, constant will be there. Also beta, that means j beta means that will be in oscillation manner, that there will be an oscillation. There will be an oscillation with a frequency of omega or sorry my dear, sorry. The fan and due to high temperature, right? Not temperature, actually humidity here, lot of humidity here. So the sweating on this on my head when the fan comes in contact, this problem arises. So For lossless transmission line, beta is equal to omega root LC, my dear. Omega root LC. Okay. And wavelength. Wavelength is denoted by lambda, which is nothing but, my dear, 2 pi by beta. It is nothing but 2 pi by omega root LC. Okay, 2 pi by omega root LC. And the unit of wavelength is nothing but, my dear, meter. Next, phase velocity. Phase velocity is nothing but, my dear, phase velocity is represented by any letter you can use, but normally VP this omega divided by beta. Phase velocity is nothing but omega by beta, and which is nothing but, my dear, omega divided by beta is nothing but omega root of LC. Omega will get cancelled, simply 1 by LC, 1 by root LC. The phase velocity is nothing but, these are some terms, my dear, for a one word question answer or in the problems. So there will be a problem like find the wavelength of the waves or the wavelength of the signal which is passing through the transmission line, such and such conditions, such and such conditions, you can find the answer. So phase velocity is nothing but omega divided by beta, and which is nothing but 1 by root LC, my dears. So we know that already. What is L? Inductance, right? Inductance of the transmission line. We already discussed the inductance of the transmission line, or the inductance of the transmission line is nothing but loop inductance. Am I right? Loop inductance of the transmission line, which is nothing but, my dear, what? 2 into 10 raised to minus 7 ln, not loop inductance, symbol inductance, right? Symbol inductance of the transmission line. Loop inductance means into 2 will be there, d by r dash. And what is C? Capacitance with respect to the ground, right? Capacitance with respect to ground, which is nothing but 2 pi epsilon divided by ln d by r, right? Ln d by r. So so this is the inductance as well as the capacitance equation. Taking the value of d is equal to 1 and solve by taking, this is no need to take and all, will cancel each other, no need to take and all. Simply substitute 1 divided by root of this 2 into 10 raised to 4 pi into 10 raised to minus 7 epsilon is equal to epsilon naught epsilon r. If you substitute these, my dears, you will nearly obtain 3 into 10 raised to 8 divided by root of epsilon 0 epsilon r. That is called phase velocity. This is the expression for phase velocity, this much meter per second. 3 into 10 raised to 8 divided by root of epsilon naught epsilon r meter per second. Okay, and for aluminium, mu r is equal to for air, epsilon r will be equal to 1. So substituting the value of here, epsilon, just a minute, my dear, just a correction, small correction. Epsilon naught epsilon r, for air epsilon r equal to 1, so that Vp will become, if you substitute epsilon r equal to 1 there, 1 divided by root of 4 pi into 10 raised to minus 7, my dear. 4 pi into 10 raised to minus 7 into epsilon is nothing but epsilon not epsilon r, which is again 4 pi into 10 raised to minus 7, correct na? Epsilon r is equal to 4 pi into 10 raised to minus. So if we solve this, 1 divided by 4 pi into 10 raised to minus 7, nearly it will be equal to 3 into 10 raised to 8 meter per second. Directly you will obtain, my dears, directly you will obtain. So this is the phase velocity. This is the equation for phase velocity. If we consider permeability and permittivity, the general expression for phase velocity Vp will be equal to 3 into 10 raised to 8 whole divided by root of mu r into epsilon r. Mu r into epsilon r. For air, epsilon r is equal to mu r equal to 1. Epsilon r equal to 1. For aluminium, mu r is equal to 1. It's very, very important. For air, relative permeability is epsilon r is equal to 1, and for aluminium conductor, that's for we are using aluminium conductor, my dears. That is the reason. That is one of the reason. It's mu r relative permeability is equal to 1. If you take iron and ore, if you take copper and ore, it will be greater than 1, so that the velocity or the signal which is not at very good speed, there may be some losses. That is the reason why we are using aluminium instead of any other conductors on overhead transmission. That is one of the reason. Of course, the cost of the aluminium is less. That is main reason. But other than this is one of the reason. So this is the concept of phase velocity, my dear. This is the concept of phase velocity. Just note it down. This derivation, no, these things are not needed actually. You just focus on this only. Okay. Okay, my dears. So that's all about this concept. Okay. Is it clear? Is there any doubt? Is there any doubt, my dears? Is there any doubt? Okay. Here na, this expression na, 2 into 10 raised to minus 7 ln d by r you can use directly, because capacitance calculation r dash is equal to r, right? So you can simply use d by r. Okay, d by r also you can use there, but a small change will be there. So that is why approximately it is equal to the speed of the light, you can say like that. Okay. So as a conclusion, you can say that this relation is actually important, my dear. Inversely proportional to mu r into epsilon r. That relationship, it is very, very important. That relationship is very, very, very important. Okay. Vp proportional to 1 by root of mu r into epsilon r. That equation you have to remember all the time. Only this equation, this relationship is only worthy from all this derivation and all. This derivation you need not to remember. Just this, my dear, just this. Next, Faraday effect. Faraday effect, my dears. Faraday effect. That is, we know that what, my dear? We know that the percentage regulation Voltage relation is nothing but sending end minus receiving divided by receiving end into 100, right? So in the transmission line, there will be a case arise. There will be a case arise at which the receiving end voltage greater than the sending end voltage. Receiving end voltage greater than the sending end voltage, called the Faraday effect. Called the Faraday effect. Called the Faraday effect. This is actually due to the presence of the transmission line capacitance. We already discussed it. In the transmission line there will be inductance as well as capacitance. So for a long transmission line, the effect of capacitance is very high than the inductance as well as the resistance. So what happens in a long transmission line? There may be a chance of under no load or light load or capacity load condition, not inductive load competition. This when the load is in capacitive or light load or no load condition. Load in the sense the end of the transmission line, that's all. What happened? The receiving end voltage appear to be higher than that of the sending end voltage, leads to the percentage voltage regulation as negative value. So this is called the Faraday effect. This is called the Faraday effect. Now we are discussing why this effect. Why this effect? Why this effect? Now this we are going to discuss. So by the ABCD parameter we can explain this. For short transmission line, so we have, my dear, for ABCD parameter consideration, we have Vs is equal to A into VR, okay, plus B into IR. Am I right, my dear? A into VR, simply short words you can use. Vs is equal to sending end voltage is equal to A into VR plus B into IR. Am I right? So if there is no load, my dear, IR will become 0. Am I right? That means this is a transmission line. If there is no load concern, it is open circuited, so that there will not be any IR. There will not be any IR. Simply the transmission line, it is ready to deliver current, but if there is no load, means there will not any current delivery. So that IR will become 0. So I can say that Vs is equal to A into VR. Am I right? Vs is equal to what, my dear? A into VR. Or I can say that Vs by A equal to VR. Vs by A equal to what, my dear? VR. For short and medium transmission line, the value of A you already obtained for the previous year classes analysis. A equal to D equal to 1. You obtained, right? You obtained, right? A equal to, for short as well as medium, A equal to 1 and 1 plus Y z by 2 respectively. Correct, na? Correct, my dear? For short transmission line you got A equal to 1, and for medium transmission line either it is in nominal T method or in pi method or N condenser method, both you obtained. In N condenser method I think 1 plus zy, but in nominal T method or nominal pi method you obtain 1 plus y z by 2. Or in short, my dear, or in short, for short and medium transmission line, A greater than or equal to 1. Am I right? A greater than or equal to 1 in both the cases. So at these cases, so if you substitute the value of A greater than or equal to 1 here, definitely Vs by A equal to VR. Na? So if A greater than or equal to 1, Vs may be equal to VR for short transmission line, but for a medium transmission line, Vs definitely will be what? That means VR definitely will be less than Vs. Is it clear? No confusion. Suppose you put A equal to 1 here, VR will be equal to Vs. Maximum possibility for short transmission line. Okay. Next, A greater than 1 is substitute here. VR will be less than Vs. Na? Because Vs by 2, suppose Vs by 1.3, it is the VR. So VR you can say that less than Vs. So for short as well as medium transmission line, there will not be any Faraday effect. There will not be any Faraday effect. That means the line will be smoothly delivering power. The output voltage, I mean the end voltage will not be greater than the what the sending end voltage. Maximum it will be equal to sending end voltage for short transmission line, but for surely for medium transmission line, the receiving end voltage will not be greater than the sending end voltage. But my dears, but for long transmission line, the value of A will be less than 1, not greater than 1 million. The value of A will be less than 1. Actually, there is also very big derivation for long transmission line. I didn't go there because of no need, which is not scope of our competitive examination point of view. Just this relationship is only needed. So for long transmission line, the value of A will be what, my dears? Less than 1. So if the value of A less than 1 means, if you substitute here, my dear, Vs by A will be equal to Vr. If the value of A less than 1 means, if A less than 1 means Vs by less than quantity, na? So we can say that Vr will be greater than Vs. If the denominator is less than 1 means Vr will be greater than Vs. This is called the Faraday effect actually. So that is why this is the theoretical explanation. Actually in physical meaning you can simply say that if the capacity effect increases, there will be Faraday effect. You can say that there will be a Faraday effect, or you can say in other words, if the surge impedance loading, if the loading of the transmission line is less than the surge impedance loading, then also there will be Faraday effect, because at that time QC greater than QL will happen. In the last class we discussed, right? QC greater than QL will happen. So then also there will be Faraday effect. So many ways you can explain the concept of Faraday effect, my dear. So now, if A less than 1 means we are definitely greater than Vs. That is the case, or that is the reason why this Faraday effect happening. Okay, so that is the reason. Okay, how can we eliminate this Faraday effect, my dear? How can we eliminate this Faraday effect? To eliminate this Faraday effect, my dear, what we are doing, we insert a reactor in load side as a shunt reactor. That means so this is the load side, my dear. Reactor. What we are going? Generator. And what we are going, my dear? We are what? Transmission line. We are inserting a reactor which having a value of X. Or XSH also you can use. XHS. Because shunt reactor. XHS we are inserting. And what is the value of that reactor, my dear, that we are going to discuss now? Value of shunt reactor. Value of shunt reactor. Value of shunt reactor. See, my dear, our basic equation again, Vs is equal to A into Vr plus B into I. Am I right? My dear? For no load condition, suppose there is no load means, again, there will not be any current IR. But if you add some shunt here, and if you switch on, if it is no load means there will not be any current. But if you add some shunt here, my dear, actually, Under this is a general diagram ideas. If there is no load means or light load condition or capacity load condition, then only there will be a Faraday effect more vigilant, more evident. But for inductive load, there will not be any Faraday effect, because that capacity effect, it will be compensated by the inductive load itself. Okay, so that is the reason why we are inserting a reactor. Reactor is nothing but an inductor. So what I am going to do, I am inserting a reactor in parallel or inductor in parallel. So what happened? Due to the presence of this inductor, the load current, that is nothing but the receiving end current, will not be zero now. It will not be zero now. It is there, some value will be there, because I already inserted that shunt reactor now. So there will be, of course, what, my dear, a receiving end current. Am I right? Receiving end current. So our aim is what? Our aim is what? We have to make the sending end current. I will say we have to make Vs equal to Vr. Am I right? We have to make what? Vs equal to Vr. It is the ideal case. Vs equal to Vr you have to make. For making this, my dear, that means substitute Vr equal to Vs in equation number 1. What I get means Vr, instead of Vs you can substitute Vr equal to A into Vr plus B into IR. Or I can say that 1 minus A into Vr is equal to B into IR. Or I can say Vr will be, or I can say Vr by IR equal to B divided by 1 minus A. What is Vr by IR? Receiving end voltage by receiving end current. Now the reactor is connected, right? Now the reactor is connected, right? So the reactor voltage divided by reactor current. That is nothing but reactance XHS, which is equal to B divided by 1 minus A. Very, very important relation. B divided by 1 minus A. B divided by 1 minus A will be the value of the shunt reactor you should add in parallel with the transmission line, so that in order to compensate for the Faraday effect, Faraday effect, you should add this much reactance in parallel, B divided by 1 minus A. That's all. There may be chances of asking question from this. What will be the value of the shunt reactor to be added? It's ABCD parameter like A and B are given. So simply you can substitute, you can find the answer. Is it clear, my dears? Is it clear? Okay. Types of conductor. First one, copper conductor. Where you are using these copper conductors? So copper conductors are using where you can use this? In wiring, right? Wiring you can use copper conductor, and in winding, right? Winding of machines you can use the copper conductor. Second type of conductor is nothing but, my dear, aluminum conductors. Where you can use these aluminum conductors? You can use in transmission line, right? Transmission line you can use the aluminum conductors, and hollow conductors or galvanized, galvanized hollow conductors or hollow conductor. Bus bar wiring you can use these hollow conductors, and galvanized iron or steel. galvanized iron or steel, you can use here rural electrification. Rural electrification you can use that because it is very cheap. That's why we are using galvanized iron or steel in rural area. Next one, cadmium and chromium. Because cadmium and chromium means, if you add, that means if you use cadmium and chromium means, even though the conductivity reduces by a small percentage, but the strength will be very high, my dears. But strength will be very high. So it is used in traction. It is used in traction purpose. Next one. That's all. So these are the type of conductors, my dear. Next, ACSR. What is that? You already know this. Aluminium, conductor, steel, reinforced. So which is nothing but, my dear, midway it will be steel and this will be the structure of aluminium. This will be aluminium, aluminium. There was, I remember still, there was one question. So ACSR is below. In mid there will be aluminium and covering it will be steel. One option. And in another option, midway it is steel and outer it is aluminium, other, and some other option also, and none of the above. The answer is midway is the steel, because why we are using this ACSR means in order to strengthen the conductor, my dear. We are in the overhead transmission line, we are using bundled conductor. We know that bundled conductor or transposer bundled conductor we are using. But its strength will be its strength will be very less, and it's less flexible also. So in order to make it more strength and more flexible, we are using ACSR. We are using ACSR, aluminium conductor steel reinforced. That means midway is steel and around there will be aluminium conductors. Very, very sorry, my dears. My health is not good today. Health in the sense, this nose is suddenly, till now there was no problem, but due to this fan, I think, or my hair might grow long. That's why I will cut it today. I will cut it off. So that is the concept of ACSR. It's simple, but you know this. Next one. Sources of electric. That means these are the things to provide Q. That means the reactive power. These are the things to absorb Q, my dear. To absorb Q. That means in the transmission system, my dear, there are many things that we provide reactive power. So the provided reactive power means there will be the effect of capacitance. There only it can provide reactive power. Something which absorb reactive power is called the inductance, and something which provide the reactive power is called the capacitance. So what are the capacitive nature elements in the transmission line? What are the capacitive nature elements? See, overexcited synchronous machine. We already discussed in the alternator session that if you excite the machine more than some limit value, then it will be act as that capacitors called the synchronous capacitor. Normally it is used for the power factor control. So in the transmission line there may be, not maybe, there will be of course some overexcited machine which is connected in the transmission line, which is act as the source of the reactive power, so that the power factor can be controlled. So this will be the source of a reactive power. And there will be static capacitor. It is again used for the power factor control and all. We are using the static capacitor and all. It may be the reason for the providing or the reactive power. Distributor line capacitor. We already discussed that in the transmission line. It is equivalent to a capacitor, right? It is equivalent to a capacitor. So there may be a chance of providing what reactive power. And capacitance of UG cable. In between underground cable also we discussed it. We are going to discuss now underground cable. So in that there will be capacitor in the underground cable also. So that also a reason for the source of reactive power. And what are the consumer of reactive power? Means what are the elements which consume the reactive power means what, my dear? Underexcited synchronous machine. Here overexcited synchronous machine may provide the reactive power, but underexcited synchronous machine can be act as the inductive load itself. So it is also a type of inductive effect. So this is also a consumer of reactive power. And transmission line inductor, of course there will be in the transmission line there will be inductance as well as a capacitance. So if the inductor is evidently responsible for the absorption of reactive power, and industrial motor, all the motor, induction motor which is connected in the transmission line is a inductive load. So that also an absorber of what? Reactive power. And static inductor for power factor connection and all, we already discussed now. For reducing the Faraday effect, we introduced a shunt reactor in the load, transmission line end. That also an inductive load. And purely inductive load, some other inductive loads also, except this. So suppose the transformer is also act as an inductive load. Transformer itself act as an inductive load, my dear. So there are chances of producing. Sometimes there are chances of producing the reactive power by some element which is likely to be in the nature of a capacitor, and sometimes there may be a chance of absorbing the reactive power which may be likely to be the nature of an inductor, and these are the things you note. Okay. Next, methods of voltage control. Shunt capacitor. Shunt capacitor. So shunt capacitor is nothing but, my dear, this is the source. And this is the transmission line. This is the load side. If the transmission, I mean if the system contains more inductive nature means the poor power factor will be the reason. We will explain later what is the drawback of poor power factor and all, we will explain later. So due to that power factor, the current absorbed from the line will be very high, so that there may be very high losses in the transmission line. So for avoiding that, we have to improve the power factor and make sure that our power factor will be nearly unity. Unity will not be obtained, I am sure, but nearly unity you have to obtain. So for that, what we are going to do, my dear, check the system nature. If the system nature is more inductive in nature, then what we are going to do, we are inserting a shunt capacitor. Remember the term, my dear, shunt capacitor. Shunt capacitor you have to insert. Shunt capacitor you have to insert, not series capacitor. In the option for confusing you, there may be shunt capacitor, series capacitor, shunt inductor, series inductor. There may be. So you don't confuse. For shunt capacitor is used for the power factor conversion, and this is used if QL less than QC. If QL less than QC, what we are going to do, if you have to introduce or you have to insert QL greater than QC, you have to insert shunt capacitor. That's all. That means if more inductive power is absorbing, then no one is to deliver the reactive power means you have to add a capacitor so that it can deliver a portion of the reactive power, so that the reactive power absorbed from the line will be reduced, because it can provide the reactive power to the load. That's all. Next, shunt reactor. We already discussed it now, right? We discussed the shunt reactor is what? Shunt reactor can be utilized to, or if, what is the condition? If QC greater than QL happens. If QC greater than QL happen, what you going to do? You have to insert a reactor in parallel to load. Parallel to load. And value of the shunt reactor, you know, B divided by N minus A, right? We already derived. Next, static var controller. Just to remember the names only, my dear. Static var controller I will explain now. That means so it is actually, this is the static VR controller, static VR controller, or simply VR controller. So hard static, no issue. So static VR controller means nothing. Here we are using a controller having, that means controlled. A circuit contains L and C, my dear. A circuit containing L and C. The peculiarity of the static var controller is that you can control the value of L and C by clearly sensing the line. That means the system will check the line. If the line is containing more inductive in nature means the capacity bank will active and compensate for that inductive will happen. If the line contains more inductive, I mean more capacitive, what happens? The inductive line will activate and it will provide the reactive power. I mean it will absorb the reactive power, extra reactive power it will absorb, and always make the system to nearly unity power factor. What, my dear? To nearly unity power factor. Okay. That's all about the power factor, method of voltage control. Okay. Method of voltage control. Next, effect of poor power factor. What is the problem of the power factor is minimum? What is the problem of the power factor is minimum, my dear? We have for a three-phase system, my dear, power P is equal to root 3 into VL IL cos phi. And cos phi is nothing but P divided by root 3 into VL into IL. Or simply I can say that cos phi inversely proportional to 1 by line current. Cos phi inversely proportional to 1 by line current. If cos phi is poor, that means less power factor, the line current will become high. If the line current is become high means I square R loss in the transmission line will become high. So that losses will be high means of course the efficiency will be less. And also IR losses that also I square R losses also high, IR drop also high. If IR drop is high means poor voltage regulation. Poor voltage regulation will be the result. Poor voltage will be the result. So these are the problems of a poor power factor. The power factor is very less means high losses will be there due to I square R losses will be high, so that the efficiency of the transmission system will be decreased and loss of the energy will be lots of energy will be dissipated as a heat in the transmission line. And also if IR drop increases, what happen, the receiving end may not get the sending end voltage, which is very very less than the sending end voltage will be received at the receiving end, so that the poor voltage regulation will be the result. So that the poor voltage regulation will be the result of such things. So what we have to do for this power factor correction? So if I increase the power factor means, and one more thing it may happen, my dear, another equation for cos phi is nothing but active power divided by apparent power. If cos phi is lesser, that means it is less means the apparent power should be high. The apparent power is high means what, my dear? The system will absorb very high amount of current from the what? Transmission line. If the current is increased means, to compensate for this increased current, increased IL, the area of the conductor should be high, correct? Because more current to carry to the transmission line means the area should be very high, otherwise the conductor may burn. Because if it had to carry a very high current means the resistance should be low. R should be R is equal to rho L by A, am I right? For R should be very low, right? For bulk power current to transfer, the R should be very minimum. For R should be minimum, the area of cross section should be maximum. Area should be maximum means we have to use thick conductors. That is again adds the cost of transmission line. So these are the problems, my dear. These are the problems of the poor power factor. That's why we are always saying that the power factor of the transmission line should be near to unity, like that. Okay? Okay, my dears. Okay. Next. Listen my dears. Listen. So now how can we improve the power factor by a capacitor, that we are going to do. Okay, how can we improve the capacitor? I already told you I can improve the capacitor, improve the power factor by inserting a capacitor in parallel. Okay, how can we improve the capacitor in such a parallel connection, that we are going to discuss now. Okay, listen. Initially the capacitors was not there my dear. So the source will provide, that means the transmission line will provide a Vs, that is the sending end voltage, and there will be a load current I. There will be, initially the IL will be same as I. Okay, initially the IL will be same as I. Okay, IL will be same as I. So, or simply you can neglect this, simply there will be a current of I. So what will be my phasor diagram for this circuit? Will be my phasor diagram. Vs, am I right my dear? Vs, and this will be I. This will be I, having power factor 5. Am I correct? Am I correct? If I add a capacitor in parallel with the system, what happen? There is always I, there will be current absorbed by the capacitor IC. So that the current will become IL. That IL is nothing but I plus IC. Yeah? The current will be drawn by the total system, from the system will be IL, which is nothing but I plus IC. So what happens means, if I add a capacitor in parallel with the load, there may be capacitor current IC, which is exactly leading the voltage by an angle line. It's a fundamental, right? So if I add a current IC here, means it is similar to that my dear, it is similar to that. The current IC can be, here also I can represent. Vector addition, vector can be placed anywhere, but the direction can't change. That is the main thing you have to note. Okay, vector can place anywhere, but this can be placed here, this can be placed here, anywhere you can place, but we can't change the direction. See, this is parallel and this is also parallel. No? That concept you have to keep it, remember. So now this will be I. So I minus IC, I minus IC will be now I real, that is I, initially I was there, now you insert the current IC. So now I plus IC, not IC, I plus IC. I plus IC will be the new current my dear, IL. So it is power factor, it is the phase angle of phi 2. Is it clear? Initially there was no IC, so simply I can say that Vs and I will be set like this. If you insert some IC there, you can insert an IC here, means I plus IC will be IL, I plus IC will be IL, that's all. So what the power factor will be what now? Phi 2. So what happened? Initially the phase angle was this much, phi 1 greater than phi 2 initially implies cos phi 1 less than cos phi 2. Cos phi 1 greater than phi 2 means cos phi 1 less than cos phi 2. Na? So now which power factor is better? Cos phi 2 is better because power factor improved. So by adding a capacitor in parallel with the load, what you are going to less phase angle will obtain now. Less phase angle means improved power factor. Less phase angle means improved power factor. And there will be an equation my dear, you simply remember this equation. The reactive power delivered by the capacitor is nothing but my dear, Q is equal to tan phi 1 minus tan phi. This is an equation my dear, you have to remember this, very very important relation. What is the reactive power delivered? Because of the insertion of this capacitor, definitely this capacitor should provide some power now to meet the inductive reactor requirement. This has to provide some reactive power, then only from the source the inductor will not absorb any power. Alright my dear, what is the function of this capacitor actually? Now, without this capacitor, there is inductor as well as capacitor. The nature of the inductor is always absorb some reactive power from the source, so that the overage apparent power of the load will be increased, so that current will be increased. For avoiding that, we inserting a capacitor in series, parallel, so that the requirement, the reactive power requirement of the inductor will be now provided by the capacitor, because the capacitor can deliver reactive power and the inductor can absorb reactive power. Basic rule. So what happens, this capacitor will provide reactive power to the inductor, so that this inductor will chupchap rahenge. This inductor will be keep silent, because it is amount, that means its requirement is fulfilled by the capacitor, so no need to disturb the source. So equal, so the reactive power delivered by the capacitance will be Q is equal to P into tan phi 1 minus tan, where P is the active power. P is the active power. Active power is always constant. Only reactive power is changing. Is it clear? My dear? Okay. Capacitor bank. In three-phase system, you can use a capacitor bank in order to provide for such a power factor correction. So power factor correction, this capacitor may be either in star or in delta. Okay, but you should note one thing, that the capacitance in star is 3 times as that of the capacitance in delta. This is simply you can obtain, because it is reverse as that of the resistance in star or delta. Okay, so you can simply check in your own manner. Take a resistor in delta and resistor in star, connect between them. That means the resistor in star will be equal to 1 by 3 as that of the resistance in delta you will obtain. So that we will check now. You have to check. Okay. This is in delta. Suppose R, everything is R. What will be star equivalent? What will be star equivalent? This value will be equal to R into R square divided by 3R. So it will be R by 3. So you can say that resistance in star will be equal to what? Resistance in delta by 3. Correct now? The opposite will happen there. So capacitance in star will be 3 times the capacitance in delta. That's it. Simple you can say. So why this is so? There is a capacitance in delta star will be 3 times as of the delta. So the capacitor is costlier than resistor. Okay. So in transmission line, power factor correction, we are using delta connected capacitor. This is also a question. Star connected or delta capacitor is normally we are using delta capacitor because its cost will be very less. Star connected means 3 times the delta capacitor means 3 times the cost also. So we are using delta connector because compared to star it will be 1 by 3 of the star only. So the delta connected, that means star connected capacitor bank will cost more. So we are using only delta capacitor bank in power factor correction. That's all. Is it clear, my dears? Is it clear? Next sag. See my dear, sag is nothing but my dear the hanging. You already observed in the transmission line that the transmission line is not steady, right? It is hanging in somewhere. In temperature, I mean in summer season it's more, the sag will be more, and winter season the sag will not be there. I mean not that much sag will not be there. So the sag is nothing but the hanging from the stable position is called the sag. And the equation for sag is equal to S is equal to WL square divided by 8T, where L is equal to distance between tower and T is nothing but tension of transmission line, that's all, and weight is nothing but weight of the conductor. Okay, so just to remember this equation my dear, just to remember this equation, WL square divided by 80, if this is for if the poles are in same position, that means in same surface. Suppose this pole is here and this pole is above some mountain and all, there will be irregularity in surface happens, and there is another equation for sag actually, but that calculation is very lengthy, so it will not expected for the competitive examination point of view, especially for AEG examination and all, because the calculation will be very lengthy then. Okay, for calculation will be very lengthy then. So simply you remember WL square by 80, that's all. So normally the question will be asked not considering, I mean not for calculating the sag and all, but S will be L square. If the length of the transmission line is increased by 2 times, weight is decreased by 2 times, tension is increased by 4 times, what happens to the sag and all? That type of question you may expect from this. That's all. So just to remember this equation my dear, it's more than enough. Okay, so that's all for today's session. So we'll meet again tomorrow. Okay my dear, so thank you so much.